Hello, this is Robert from Microchip. In today's video, I'll be discussing how to model the performance of the integrated OPAMP peripherals in MPLAB Mindi Analog Simulator. Then, I will do a simulation versus real-world comparison of the circuit to see how close the two are. Source code and the Mindi schematic for this video are available in the links below. Mindi is a free tool that Microchip provides for modeling analog circuits. You can find a download link in the video description. Before we can simulate the integrated operational amplifier, first we need to install the OPAMP model. Models are available from the Mindi software libraries page. First, go to microchip.com/Mindi. Then click on the Mindi software libraries button. From here, search for the device, in this case a PIC18F56Q71. Note, all devices in this microcontroller family use the same model. On the download page, make sure to grab the Mindi model, not the SPICE model. The SPICE model is provided for use with third-party tools, whereas the Mindi model is designed for use with our tool. After downloading the model file, drag the file into the command shell window of Mindi. You should see a prompt to install the model. Since the microcontroller runs on a unipolar power supply, or in other words, a supply without a negative rail, signals must remain positive. This means offsetting the sinusoidal waveform used as input. Additionally, the input must remain within the absolute maximum ratings of the device. If we apply a signal outside of the ratings, then the microcontroller may become damaged along with anything else in the circuit. Next, I need a circuit for the comparison, which I created and linked in the description below. For simplicity, I will build a non-inverting amplifier with a gain of 2. With external parts, you'd specify the resistors used for feedback in this circuit, but since I'm using the internal resistor ladder, we cannot control the resistance of each resistor. Instead, we control the ratio of resistance in the ladder. Table 44-2 in the datasheet shows the ratios of resistance that are possible in the microcontroller. To get a gain of 2, we need to use this configuration that I've highlighted on screen. However, in the simulation, we need to convert from the ratio to absolute resistance. As noted in the margin of the table, there is a nominal resistance of 20K per unit, which equates to 160 kiloohms of resistance for each of the resistors. Next, let's set up the microcontroller. From the code example in the video description, you can download the hex file directly, or you can compile from source code. This video will show the drag and drop hex file method, which can be done in only a few seconds and without installing the IDE. First, go to GitHub and click on Releases. Select the latest released version and download the zip. Then, extract one of the hex files. Either of the compiled versions will work. Plug in the Curiosity Nano to your desktop computer, then drag and drop the hex file onto the drive. The Nano will upload the program to the microcontroller. Programming is successful if the yellow LED on the Nano starts blinking. My signal source for this comparison is a function generator. I'm using a BNC T-junction to split the output. One output will go into the oscilloscope, while the other goes into the microcontroller. The output of the OPAMP is captured with a 10x probe. This setup isn't ideal for high frequencies, but since we're only at a couple megahertz maximum, the signal integrity should be sufficient for a comparison. From a casual glance, the two waveforms on screen appear nearly identical, which shows the power of analog simulation. But if we take a closer look at the behavior near ground, you can see the analog simulation deviates from the actual device. The actual device has a much smoother response curve, although there is still error around the same location. Thank you for watching this video. More information about the PIC18F56Q71 family of microcontrollers is available in the video description.